Introduction to Statistical Inference, Statistical Testing, and Confidence Interval Estimation. In this program, we'll learn how to use the Z procedures to run a test of significance or hypothesis test for the population proportion. We'll also use the 95% confidence interval to estimate the population proportion. We could do the same thing for the population mean. We'll use the same Z procedure to run a test for the population mean and the confidence interval to make an estimate for the population mean. We'll also demonstrate how to do minimum sample size calculations. For example, a problem could read as follows. In the past, the credit card company has assumed that the entire market or the entire population of cardholders is 50% men and 50% women. We're going to test to see if this assumption needs revision, and if so, what revision is needed. To run this test, we're going to use the Unit 2 Excel tool, Probability and Intro to Inference. We're going to have to first specify what variable we're using for our Z-test for proportion. And we know this has to be a test for proportion because we're working with gender, and gender is categorical. When we're working with categorical data, we'll test the proportion by specifying the variable number 4 and the success category F. It really doesn't matter if we use M or F. That's just going to determine the p-hat value that we're comparing to our assumed value of 50%. Once I input a variable number and a success category, I'll see my sample information on the worksheet Z-test for proportion. And we could see that our sample of 109 cardholders has 60 women. The sample proportion p-hat is 0.5505. We'd like to test the assumption of 50% women. So to formulate the null hypothesis, I simply input 0.5 as an assumed population proportion. When I hit enter, my results are shown. So what do the results show? Well, first of all, we see that our test statistic Z is 1.054 rounded. This tells me that the sample proportion 0.5505 is 1.054 standard errors of proportion above 0.5. In other words, p-hat is 1.054 standard deviations of p-hat above 0.5. In order to achieve statistical significance at the 5% alpha level, my Z-score, or test statistic, would need to be at least 1.96. Ours is not. P-hat of 0.5505 is relatively close to the assumed value of 0.5 and gives us no reason to reject the null hypothesis. Our two-tailed p-value expresses the same thing as the test statistic. In other words, it's showing, in this case with a probability, whether our p-hat value differs significantly from 0.5. When the p-value is less than alpha, we reject the null hypothesis. Here, the p-value is very high, 0.2921. Here the p-value is quite clearly greater than 5%, so it's leading us to the same conclusion do not reject the null hypothesis. In other words, the assumption of 50% women, and therefore 50% men, still seems to be valid. Now let's look a little bit more carefully at our test statistic and the two-tailed p-value. We call this a z-test for proportion because the sampling distribution of p-hat, sort of behind the scenes of our test, is what's being used to obtain a one-tailed p-value and then doubling that to obtain the two-tailed p-value. All normal probability, as we've seen, really reduces to the distribution of z-scores, or the standard normal probability that has a mean mu of 0 and a standard deviation sigma of 1. Now my software will do this for me. We never have to use the normal probability calculator in the way that I am. We're just looking at it this way to better understand the test statistic and the two-tailed p-value. We could see that the probability on a normal curve of being at least 1.0536, that's my test statistic, right? The probability of being at least that far above the mean on a normal curve is 0.1460. The two-tailed p-value has to double that. So 2 times 0.1460 is how the spreadsheet is obtaining the two-tailed p-value of 0.2921. In other words, what's the probability of being at least this far above the mean or at least that far below the mean? 2 times 0.1460 with difference due to rounding, Excel is calculating as 0.2921. So quite clearly, the results of our test would be do not reject the null hypothesis. We could base our decision on either the test statistic. The test statistic is not more extreme than 1.96, either positive or negative. It has to be at least 1.96 in order to reject the null at the 5% level of significance. We could also use the p-value. The p-value is greater than 5%. We need the p-value to be less than 5% in order to reject the null hypothesis. So based on the p-value or the test statistic, we get to the same conclusion, and that is do not reject the null hypothesis. In other words, the assumption of 50% women still seems valid. Our 95% confidence interval also supports this decision. We are 95% confident that the population proportion of women in the entire population, the population proportion of women is somewhere between 45.7% and 64.4%. We could see that our estimate for P includes the value 0.5. This will always happen. If we fail to reject the null hypothesis at the 5% level of significance, alpha, 5%, our 95% confidence interval will always include our test value, here 0.5. Sometimes we could use our confidence interval as a constraint to determine the minimum required sample size in order to achieve a particular margin of error. When we do minimum required sample size calculations, if we're working with proportion, we have to use the solver macro in Excel. It's very important to understand that when we're using solver, we don't want anything to be in column E. So anything that we input on the data page that's making sample information appear in column E, we would want to remove. We'll input our sample information directly into column F. These are cells that we could change easily without disrupting the function of the Excel tool. For example, we currently have a sample of 109 cardholders. And of those 109, 60, or a proportion of 0.5505, are women. Our 95% confidence interval has a margin of error of 9.33%, plus minus. Now we're going to target a margin of error of only 8%. In order to narrow our confidence interval, we need the sample size to increase. As sample size goes up, standard error goes down, and the resulting confidence interval will narrow. How much of an increase in n is needed to achieve that target margin of error of at most plus minus 8%? If we select Solver, we could see that the solver is set up to do this calculation for us. Our objective cell, G29, is the margin of error. We could specify to what value we would like that to be set. We're going to set the margin of error to a value of 8%. And we're going to do that by changing the sample size and the number of women. We have to change both of those so that we could maintain the constraint that p hat stays pretty close to the value 0.5505. So we're setting the margin of error to a target value of 8% by changing F6 and F7 simultaneously, subject to the constraint that p hat stays equal to 0.5505. Once we get our solver parameters set up, we could click Solve. Solver did find a solution. Minimum sample size calculations always round up. So our answer here would be n equals 149. In order to achieve a margin of error of at most 8%, we would need a sample of at least 149 cardholders. Sometimes we're running a test about a categorical variable. When we're working with categorical data, the correct procedure would involve p hat, the sample proportion, and an assumed value for p, the population proportion. These are percentages, relative frequencies. These are techniques that we would associate with categorical data, which is why we just ran a z-test for proportion. However, quantitative variables can be averaged. So we could run the same z-test, only now we'll run the z-test for the population mean. For example, in the past, the credit card company has assumed that the population mean income is $125,000. Test to see if this assumption needs revision, and if so, what revision is needed. The z-test for the population mean technically always assumes that sigma, the population standard deviation, is known. Here, we're given a value to use as our assumed value for sigma, 45,000. To run our z-test for the population mean, we need to tell our Excel tool what variable we're using. We're testing income, so we're going to use our sample data on income, variable number 1. We were also given to use an assumed value for sigma equal to 45,000. But remember, our data on income are already in thousands of dollars. So we do not input 45,000, but rather 45. The worksheet tab z-test for the mean is what we need next. We're testing the assumption that the population mean is 125,000. So we input a test value of 125 to define our null hypothesis. Now our results. Our results tell us that the sample mean of $133,872, or 133.872, is 2.058 standard deviations of x bar, or what we call standard error of the mean. This is the standard deviation of our normal sampling distribution of x bar. Okay, our z-score is telling us that the sample mean is 2.058 standard errors above 125. In other words, if we were to calculate this manually, we would say 133.872 minus 125 divided by 4.3102 equals 2.058, showing that our sample mean is 2.058 standard deviations above 125. This is a statistically significant difference. Our sample mean is significantly greater than 125. Remember, we're defining the level of significance with alpha. Alpha is equal to 5%, half in the upper tail, half in the lower tail. So our critical value, z star, is always 1.96. Very simply, we could compare z to z star and determine whether or not we reject the null. Here it's greater than 1.96, so we do. The two-tailed p-value can also be used. Our two-tailed p-value of 0.0396 is less than 5% alpha, which leads us to the same conclusion: reject the null. Confidence intervals are two-tailed, and they should agree, therefore, with our two-tailed test results. And here, that is the case. I am 95% confident that the population mean income is somewhere in the range 125.42 to 142.32. The entire confidence range excludes the value 125. This is part of why we're rejecting the null hypothesis that mu equals 125. Our results will always agree. If our test statistic is beyond 1.96, our p-value must be less than 5%, and the test value for mu must be excluded from the confidence range. Remember, as this is a z-test for the population mean, everything reduces to a standard normal probability distribution related to our z-score. The z-test statistic for our income test was 2.058. The probability of being at least 2.058 standard deviations above the mean is 0.0198. But we want a two-tailed p-value. So what we want is the probability of being at least that far above or below the mean. So we would need 0.0198 plus another 0.0198, which is how we're obtaining the two-tailed p-value of 0.0396. Determining the minimum required sample size to achieve a target margin of error for our confidence interval estimating the population mean. We can use goal-seek, and this is much simpler than using solver. We're only changing one thing, n. So there's no constraints, and a simple goal-seek is all that we need. However, it's important to note that we do not want anything input on the data page when we're doing minimum sample size calculations. Rather, we'll input our sample information directly into column F. Here our sample is 109, our sample mean 133.872, and we're using an assumed value for sigma equal to 45,000, or simply 45. Our goal-seek table is at the bottom of the sheet. We begin by inputting the current sample size. Goal-seek will not work if this is empty. Goal-seek has to begin with some value in the cell being changed. So we input 109, and we could see that our current margin of error is 8.45. These are in thousands of dollars, so the margin of error is plus minus $8,450. What would be the minimum required sample size to reduce that margin of error to only $5,000? The goal-seek will tell us. Tools, goal-seek, and we would like to set the cell E36, the margin of error, to a value of 5, because remember, our income data are in thousands, by changing cell E37, our sample size. When we click OK, the goal-seek will very quickly return an answer of 311.05. However, minimum sample size calculations always round up. So the actual answer would be 312. Let's see if we input 312, whether we could get this margin of error to change to 5. So if we go up to our F6 cell, where we currently have 109, we'll simply change that to 312 to check our answer. And we could see that we meet that target margin of error of plus minus 5. The only reason we're not actually equal to 5 exactly is because we're rounding up to 312. Obviously, we have to round up because we can't take only part of a card holder in a sample. This concludes the video, Introduction to Statistical Inference, Z procedures for proportions and means.